A smartphone camera is honestly one of the most innovative devices humans have ever created. And I don't think most of us realize how cleverly these tiny machines are actually put together. So, in this video, I'm going to walk you through how a smartphone camera actually works, and hopefully, you will learn a thing or two. First of all, let's talk size. A camera module is typically shaped like a square or a rectangle with dimensions being anywhere between 6 millimeters to 8 millimeters in length and width, and about 4 millimeters to 8 millimeters in depth. That's a very tiny amount of space considering the amount of technology that gets packed into it. Simply put, a camera just converts light into image. So naturally, it needs to be able to control the amount of light that gets into it. And this is where the aperture comes into play. Given the space constraints, most camera modules have a fixed aperture size. But higher end smartphones actually have a very clever mechanism with which they can change the aperture size quickly and precisely. Picture this: the mechanism contains several aperture blades arranged in a perfect circle. Each blade can rotate around its own pivot point, and when all the blades rotate together, you get this beautiful, precise aperture control system. It's like a tiny mechanical iris opening and closing. The rotation itself is powered by two electromagnets that cause the blades to move, plus a Hall sensor that keeps track of exactly where the blades are positioned. Now that we understand how the amount of light is controlled, we need to look at how this light falls onto the camera sensor. And boy, that's not an easy task at all. Here's the thing: there are always imperfections in how a lens focuses light. These are called aberrations, and they can cause all sorts of problems like blur, color fringing, distortion, and something called coma. So, modern cameras don't just use one lens. Instead, they use a group of tiny lenses, and each one helps fix a different problem. How many lenses, what shape they are, and exactly where they sit. All of this is carefully calculated using optical design and ray tracing software. The goal is to make the whole group to work together to create really sharp images and be able to manufacture at scale. All right, now for the fun part. So far, we have managed to control the amount of light that gets into the camera and have those light rays exactly where we want them. Now it's time to take these perfectly aligned photons and convert them into an actual image. Since we want color images, the camera needs red, green, and blue information. But here's the catch: each single pixel sensor does not measure color, it measures only light intensity. So all cameras have a filter layer on top called as the CFA. It's called color filter array. The most common CFA is the Bayer filter. It's basically a grid of tiny red, green, and blue filters arranged in a specific pattern, usually RGB. So green appears twice as often as red or blue. For example, let's assume that we have a yellow color ball. This is the actual image. Now, if I open the actual ball and really zoom in, you don't see anything that different. Let's quickly look at the raw sensor data. Now, by default, you can see that it looks green in color and does not have the original yellow color. However, if you zoom in, you will actually see that it just takes the RGB pattern that we have had. And now, how do we reconstruct the color image? Well, you can do a simple bilinear interpolation. And if you do that, this is what the result is going to look like. All right. So now you can see that this image looks like our original image. And if I zoom in, you can clearly see that there's no pixel information. But this simple averaging doesn't work in corners. You can see that in edges, especially edges that are not aligned with your Cartesian frame, there is actually a discoloration for which slightly more advanced algorithms have to be used. One thing we have not talked about much is how a camera converts light into intensity, which later become colors. Think of it like a solar panel, but way more precise. Each pixel in your image sensor converts light into electrical charge. When you are taking a picture, all the pixels collect charge while the shutter is open. And this gives you the intensity value for each pixel, which then gets converted into your final image. The final piece of technology I want to talk about is optical image stabilization. Here, the camera basically understands how your phone is actually moving by reading the gyroscope values, and it uses mechanical actuators to move the camera components in the opposite direction, and this results in a stable image or video. Higher end smartphones use shape memory alloys as an actuator. The really interesting thing about shape memory alloys is that you can change its length by passing electric current through it, because these are temperature sensitive and they act very fast. In this animation, the wires are actually made up of shape memory alloys, and by actuating the right pair of alloys, we can get the camera to translate along x-axis, along y-axis, rotate about x-axis, and rotate about y-axis. By using a combination of these four moments, the camera can stabilize itself. Alright, we are finally at the end of this video. I hope you enjoyed the presentation today. Alright, thanks for watching and I'll see you in the next one.